Okay. Hi, my name is Tom Sandri. I'm Technical Director here at Protec Equipment Resources. And what I'd like to do today is introduce you to one of our new investments in our rental inventory. It is the Megger PFL22 cable fault locating system. The system does have some notable improvements over previous models that we had in our rental inventory, the PFL20 series. Some of the things that I particularly like about this particular model, it is a completely self-contained instrument. The lower portion comprises of your high voltage surge generator. It has an output capacity for 0 to 16,000 volts on surge discharge or thumping. Also has capability of going 0 to 20,000 volts for doing DC proof testing. Also housed within the same is your arc reflection or cable radar based coupling devices, which will support both the arc reflection, the pulse echo, and impulse current techniques of time domain reflectometry. So all of that coupling comprised in the lower section, along with all of your high voltage thumping and proof burn testing capabilities. The top unit, which has a flip-up lid, houses the actual circuitry for the time domain reflectometer system. So again, it is all self-contained. A system of this size, ideal for basically 15,000 volt type of cabling services, up to about 25,000 volt cabling services. Also very useful for large industrial or potentially wind farming applications where we get cable faults or breakdowns in the buried services. Moving over to the side panel of the instrument, again, a nice feature that we see over here is the primary power source for this instrument is AC 120 volt service. However, Megger does have the built-in provision where it will accept a DC input. Built into the instrument there is a DC to AC inverter. So if we're, for instance, working at a wind farm, we don't have power up, we can actually run this instrument by simply connecting the DC source onto the 12 volt battery of our truck, and we could actually run the instrument in the field without any local power available. Another very nice feature on this particular model, all interfacing cabling going from the radar to the high voltage unit is all nicely kept neat and safe in this housing here. And also the high voltage cables are detachable. A wonderful, wonderful innovation, particularly for thumpers. Many of the earlier generation thumpers that you'll see on the marketplace, the high voltage cables are permanently attached and terminated within the chassis of the surge generator itself. This basically means that you have coils of cable on the back of the instrument. If damage occurs at any time to your output cables, you're in essence sending a 200-pound unit back to the factory just to have repair done on the cable. I think Megger scores some very high points here by having a detachable cabling system. It lends the ability to go ahead, remove, keeps the instrument nice, clean, ergonomic for loading and unloading to and from a truck, nothing to get snagged or damaged or destroyed. Also gives a customer the option to have different cabling options. They may invest in a short cable length, they may invest in a longer cable length, replacing cable, or if cable gets damaged, thumper stays behind, just the cable goes off to for repair, or a replacement is brought in. Finally, moving to the last side panel, we have our main system earthing. So on this connection here, if I'm using the system in the field on the ground, I will basically run a ground from here to the utility system ground. If I'm running it from the back of a truck, I'll run a ground from here to the chassis of the truck and from here to the utility system ground. This little plug serves as the system interlock. When the plug is pulled out, For safety purposes, I can take this along with me. The instrument will not engage, will not go to a high voltage state until the interlock is once again returned. Moving on to some of the internal elements. As we see here, this panel serves as your control module to your high voltage and your radar coupling devices. The way that the switches operate is a pull up to undo the connection, rotate to the setting, and replunge back in to set that setting. You have the mode select section over here, which will in essence allow you to do either coupling to your radar devices, arc reflection, time domain reflectometry, or pulse echo mode, or to do your thumping or high voltage direct mode, where surge would be direct thumping, and or to activate your internal DC proof tester or burn down circuit. Over on this control knob we have the voltage range. The PFL22 is what we refer to as a constant energy thumper. The concept of a constant energy thumper is to allow the person the ability not only to adjust voltage, but also to adjust the internal capacitance. Here, energy is what we want to deliver to the fault to get successful breakovers, to get good strong arcs for our radar coupling. What we want to limit is the amount of voltage that we're applying. The voltage is the stressful element, particularly in a service age cable. So in a constant energy thumper, by giving the client the ability not only to adjust output voltage, but to also adjust the capacitance, what we're able to do is on the lower thumping ranges, utilize larger capacitance, deliver maximum amount of energy at the lowest possible thumping values of voltage. So we have two ranges, 0 to 8,000 volts and 0 to 16,000 volts. Both will set different capacitive values. The lower thumping range uses the larger capacitance. The higher thumping range uses a slightly lower capacitance, delivering the same total amount of energy of 1,500 joules at the maximum output of either range. We have the DC ammeter, the DC kilovolt meter. So again, if we're running a proof test, we can monitor the voltage that the circuit is holding. We can measure or document the amount of leakage current or fault current flowing. Also, when we're setting up our capacitive discharge, we have a voltage preview mode where we could actually bring the internal charging circuit up to the desired level, initiate, then charge the capacitor to that preset previewed value and discharge. Megger has also done a very nice job of giving safety interlock notifications. If any of the top panel control settings are not done to the safety performance of the instrument, the associated lamp will illuminate, immediately alerting the end user that check your mode switch, check your range switch, may not be properly seated, check your high voltage cable, is it properly plugged in and connected, check your zero inner start, or check your external remote and interlock switch. The upper lid serves as the housing for the TDR 100, the time domain reflectometer. The instrument does offer a USB capability, so files can be loaded to and from a memory stick for later generating reports for our clients. Next, we'll go ahead, hook up, and I'll take you through an operational procedure. Okay, we've got the cables and everything of our PFL22 system all hooked up. Our test fixture basically is just a wall-mounted spark gap so that we're able to go ahead and deliver surges to it, validate that the instrument is discharging properly, we're getting proper discharge and energy transfer. We can also do the proof burn down technique, make sure that all the circuitry is working and functional on that. I have approximately 200 feet of cable connected up to this as well. So I can also test out the radar, make sure that we're getting proper radar patterns, that we have the open gap, do the arc reflection test, make sure that it sparks over, the radar triggers, gives us the updated high voltage picture. So this is the way that when the unit comes back in from a rental, we're going to go through and just validate that everything within the high voltage system, within the radar coupling, and within the radar unit are all operating properly before going out to our next client. Now, on the PFL22, you will notice that your on-off switch is the exact same as your emergency stop. So if you're looking for an on-off switch, a traditional rocker panel switch like we have here on the radar unit, you're not going to find it here. To actually turn the unit on, you go to your emergency stop, just pull straight up, and that will in essence turn on the unit. When it's time to turn the unit off, or at any time during an emergency stop procedure, just slam down on your mushroom head switch. That will turn off your system. Now you'll notice that the MTDR does have a separate on-off switch control. Not always will you be in the field using the radar. You may be just going into the field just to do proof testing. So again, we have a separate on-off switch for the radar unit. Now you'll notice that to change a mode setting right now, I see the two blue lamps indicating that my mode select switch is currently positioned and set for the internal radar coupling. So if I'm in arc reflection, I will have both the high voltage unit and the low voltage unit simultaneously connected to the cable under test, and I will be able to use both devices simultaneously. If I select just the TDR mode, it will still allow the radar to be coupled through the internal coupling circuit to the cable under test, but in the TDR mode, it will lock out and prevent the high voltage unit from going hot. So, purpose for the TDR mode, maybe it's a three-phase circuit, maybe it's an acceptance test, and all I want to do is document the three phases, capture the waveforms, take a look at the installation, the splices, etc. But I do not want to run high voltage, and I don't want the operator to be accidentally hit with high voltage. So mode select would be set to the arc reflection TDR mode. The appropriate button for TDR would be pushed, preventing high voltage from being brought into the circuit. If I'm doing a high voltage breakdown test and I want to be able to capture the point of where the cable flashed over, I would simply select the arc reflection mode. Again, it allows me to use the radar, allows me to use the high voltage surge generator simultaneously. If I want to change mode and I want to go to my direct functions of direct thumping or my proof burn mode, I simply lift up, rotate, and reset my switch. Now you'll notice that the blue lamps are illuminated over here. So at this stage, it merely tells me that I've selected this section, but now to select a specific technique, I'd merely push the button, and you may have noticed that the mode select simply set to this position tells me that these are my two potentially active modes of operation. The system is in a safe earth-grounded situation where, again, this would be where I can safely handle the cables, safely make connections or disconnects. Once I select a technique, you'll notice that the system goes to an ungrounded and potentially high voltage on condition. I have a zero interlock. If this was not set, I would get a warning over here saying the system will not go live until I go ahead and I initiate my zero interlock. Now, to run a proof test, I have the mode activated. You'll notice that the initiate lamp comes on and it's green. So all parameters are all set up that the instrument sees itself in a safe and ready mode to use. I push the initiate. The flashing green tells me now I can start performing my test. So watching my kilovolt meter, I'm going to slowly start to elevate my output voltage. Now, when I reach a point of breakdown, any further advances of my voltage control will only provide me higher fault current. So in essence, I've now left the proof mode and I'm now in a burn function. And we can see the burn down occurring at our electrodes. I'll bring my voltage back to 0. I know that my spark gap is flashing over at approximately a 5,000 volt level. At this point, to end the test and to go back into a safe ground condition, I merely repress my proof burn, I disengage my high voltage, and I go back to a safe grounded state. If I want to now implement a direct thump or a thump test on the cable, I merely select surge, system goes to an ungrounded state. I can adjust my cycle either for a single shot where the instrument will not discharge until I press the initiate button, or I can set it for a time sequence up to 30-second delay. I'm going to go ahead and just set it for a nominal time sequence. Notice that the blue lamp tells me that I'm right now in a preview state. In a preview state, it allows me to go ahead and dial up to a level of voltage that I want to discharge at. I'm going to do it at approximately 6 kV. When I actually want to perform, I will then hit the initiate key. You'll now notice that the surge generator will charge itself to the preview value and will discharge at my spark gap. When I want to end the test, I'll bring it back to 0 start and merely press my surge key one more time, and I'm back to a safe grounded state. That's the simple way of testing your output circuitry for your proof burn, making sure that you are delivering proper output voltages as well as burn currents, and also for testing your direct thumping, making sure that all of the high voltage connections are in place and we're actually delivering the proper energy to the circuit. The next thing that we'll go through the arc reflection and TDR. For that, we're going to turn on our radar system. It is a embedded Windows operating system, so like most computers, it's going to have a little bit of a boot up time, so we'll wait on that. Okay. At this stage, you'll notice that I'm still in my direct surge and proof burn mode. So on my radar, I'm still not seeing to the cable under test. I know the radar is working because I'm getting the outgoing reflection, or what we normally refer to as the transmit pulse. That's the energy leaving the MTDR 100, but I'm not seeing anything on the cable. So I will lift, rotate my mode select, engage the internal radar coupling. As I come over here to test, notice that by rotating this knob, I can change any of my selections. By pressing, I can activate. So I've just run a TDR test. Here I can see the end of the cable, I can prove that it's the end of the cable by applying a shunt or a short circuit to that point. And just excuse me while I find a tool to apply a short circuit. An open end of cable or open circuit will be an upward reflection. A shorted end or grounded will be a negative reflection. Now, as I mentioned before, if I select TDR as my technique, the system will go out of ground and it will apply the red bars, but notice that the initiate lamp will not illuminate. So what the instrument is reporting back to me is that I am no longer in an earth grounded state on my high voltage system. I am in an elevated test mode. However, I cannot apply any high voltage. So if the operator is now handling the test leads and is making a change from phase A to phase B to phase C and so on, they can do so safely. To exit the mode, again, you just push the button a second time. We're back to the grounded state. To run the arc reflection test, I simply select arc reflection. Again, I go to an elevated test mode, but notice now my initiate lamp comes on, allowing me access to the high voltage system. Now, for an arc reflection test, I do like to work in a single shot. We will go ahead and cancel the low voltage TDR test by simply pressing down on the knob. I will now go to my arm, and the way arc reflection works is we actually take two pictures of the cable. The first picture is with just the low voltage high frequency energy of the TDR radar capturing events along the cable path. I can see the end of the cable, I can see my connection to the cable, I can see my instrumentation or my energy leaving my radar. During the high voltage test, what I want to do is I want to capture the arc that is created through the discharging of the energy through my test gap. So arming the system, basically then, the instrument will go to arm, my low voltage image will be frozen to display memory, and the instrument is waiting for a trigger event before it starts to update the patterns. You'll notice that I'm in a voltage preview mode. I'm going to elevate my output voltage to the same 6 kV that I used before. And when I'm ready to run the test and to capture the event, I merely come to the initiate key, depress it. My radar will charge, discharge, and the red waveform indicates my high voltage pattern. The negative reflection shown is the short circuit that is caused during the arc. If we want to control our cursors, we simply rotate over to cursor, depress once. We have access to the right cursor. Notice that the position of the cursor is clearly spelled out in feet. If I wish to adjust or move my left cursor, I merely depress my knob one more time, activate my left, and I can always take measurements between these 2 points. For normal operation, this will be preset by Protec, and your left cursor will be at the position of the end of your output test lead. As we move through to preferences, the PFL22 combined with the MTDR100 does allow a auto fault location where the instrument will automatically select the range, the gain, will try to find the end of the cable for you, and after a high voltage discharge will try to find the flash point and adjust the marker accordingly. So the unit does combine a nice mixture of both automated fault locating for those infrequent users as well as manual control of the instrument for a more experienced user. We do have an internal memory which will give us cable types. So if I'm looking for setting the velocity factor on my radar, I can go through the internal library, find the type of cable that I'm testing, and set the appropriate velocity of propagation factor. Modes of operation. Here's where I can change the radar from the arc reflection style radar to just low voltage TDR, which will allow me 3 waveforms, one for each phase of the circuit. I can do the impulse current technique, a technique referred to as loop off, loop on, and also voltage decay. So again, a rather simple user interface, very intuitive, combined with a rather simple high voltage user interface, rather intuitive. Thank you for your time. Hope you enjoyed this short presentation.